This is the PL number 3 of theory of structures. In this PL, we're going to solve an open rigid joint structure. Here we have the structure and the data to solve the exercise. We have three different questions: the indeterminacy degree, the diagrams, and the rotation at D. The indeterminacy degree is going to be calculated as the external indeterminacy degree plus the internal indeterminacy degree. As this is an open rigid joint structure, this internal indeterminacy degree is going to be 0, and we are just going to have the external one. The external one is calculated as the number of unknowns r minus 3 minus a0. A0 states the number of hinges minus 1. In this case, as the number of hinges is 0, a0 is 0. So the indeterminacy degree is 4 minus 3, 4 because we have 4 unknown reactions, minus 3. So the indeterminacy degree is going to be 1. This is going to be taken into account to calculate redundance. As the indeterminacy degree is 1, we are just going to have 1 redundant. So we have 4 unknowns and only 3 equilibrium equations. We are going to have to apply the force method to calculate these forces. So first of all, we need to determine the statically determinate structure. So to do that, we are going to remove the spring. We remove it from the structure and we introduce a force x1. Now, this force S1 is going to be calculated by the compatibility equation, which relates the system 0 with the system 1, which are going to be explained later. And by calculating this force, we can draw and obtain the different forces. So we're going to start with the system 0. The system 0 is basically the structure, but removing the spring and without any force in this point, in point A. So if we apply the equilibrium equation, we don't have any vertical nor horizontal force, so reactions here in this support, this fixed support, are going to be 0, and we are just going to have a moment here, which is going to be the value of m, but in the opposite direction. If we draw the bending moment diagram, we are going to obtain something like this. Here we have a jump due to this moment applied, and as we don't have any other forces, this bending moment keeps constant during all the beam. Finally, in the horizontal part, we have also this bending moment diagram, but when it reaches this point where we have the moment applied, it goes up to the value of 0. In the system 0, the shear and the axial forces are both 0, as we do not have any. Now, the system 1 is the system which is obtained by introducing the force S1, x1 equals to 1, and removing the other force, the moment. We don't have, in this case, the moment. So we calculate the reaction at the fixed support, and we have a vertical force of value minus 1, there is no horizontal force, and a moment of value L. If we draw the moment, we start by this end. In this part, the moment is 0, but as we have a force equals to 1 applied, as we advance in the right direction, this value is going to increase till the value of L. So the lower part is going to be under tension, so the diagram is going to be drawn in the lower part, and finally in the vertical beam, the tension part is going to be the right one, as this value of L is the intention is also here, and we have no shear forces there, so the bending diagram in this zone is constant. Then the shear diagram. Here we have a force equals to 1 applied, so we have a jump, then it keeps constant till we reach this point where the value decreases to 0 again. Now the axial force diagram is just this part, which is gonna be under compression. So now, as we have calculated the diagrams for system 1 and system 0, we can calculate the components of the compatibility equation. The first component is calculated by the forces of system 1 and displacement of system 0 by a multiplication of diagrams. In this case, it's important to tell that the spring has no effect, as the force on the spring on the system 0 is equals to 0. It's also remarkable to state that it's important to take into account the curvature, as the difference in temperature in the vertical beam creates a deformation, a bending deformation, which must be taken into account in this part of the equation. So we multiply the bending diagram of system 1 times the bending diagram of system 0, and we obtain the following multiplication, and also we need to take into account the effect of the curvature. So by multiplying and using the table of multiplication of diagrams, we get the following multiplication. This first one is a multiplication of rectangular bending diagrams, and the second one too. It's important to take into account the negative sign in both sizes. T times alpha H times L, and we obtain a value of minus 1.6642. Now we do the same but for the component 1, 1. In this case we multiply the forces of system 1 times the deformation of system 1. In this case the value of the spring is not 0, as the displacement of the spring is the force on the spring over the constant of the spring. So we perform the multiplication of diagrams. We obtain the following. This is just by obtaining the values from the table of multiplication of diagrams, and by applying the following multiplication by introducing the data given by the problem. As 0. At this point, we can calculate the value of x1, as x1 is equal to minus the component 1, 0 over 1, 1. So here we have minus 1.66.2, 0.01428. And so we obtain a force S1 of 116.54 newtons. Now, at this point, we are able to calculate the diagram of moments of the structure just by applying the superposition theorem. M equals to M0 plus M1 times X1. And for the shear and the axial have the same thing, 0. So now we are gonna calculate the diagram of moments of the structure. Here we have a force X1 applied, so here we're gonna have a moment value X1 times L. Oh, sorry, I forgot to tell you that the sign of x1 reveals that the direction was as supposed, in the upper direction. This value is here. Now, if we start by this side, here we have the moment equals to 2 kilonewtons, which is going to be kept constant till this value here. And here we have M This is just by applying the superposition theorem to the diagrams, so we can obtain their value. Well, this is just one for calligraphy. And finally, for the axial diagram. Axial force diagram, it's going to be under compression. It's going to have a value of x1. Now, we have the bending, the shear, and the axial diagrams. So now we are asked to calculate the rotation at D. To do that, we will apply the method of unit load. Now, we're going to apply a moment of value 1 to the statically determinate structure value 1. Now we are going to calculate reactions. We will obtain here a moment of 1, value equals 1, and the vertical and horizontal reactions are going to be 0. So now the virtual moment diagram. Here we're going to have a jump due to this moment. It's going to be kept constant. The part in tension is going to be the right part of the beam. Now here we're going to have also, this part, upper part is going to be under tension. Here, this moment will make a jump to make the diagram equals to 0. So now we apply the method of unit load, principle of virtual works, which states that the external work equals the internal work. In this case, external work is equal to 1 times the rotation at D, and the internal work is equal to the virtual moments times the bending moment in real plus curvature real dx plus the effect of the spring, which in this case is going to be reaction virtual and reaction real over Sm. As reaction virtual is 0, the effect of the spring is 0. We calculate now the multiplication of bending diagrams. we obtain the following. In this part, it's important to take into account the sign of the different diagrams. And also take into account the curvature, which may be forgotten while performing the exercise. The curvature, in this case, is 2 times t times the coefficient over h. And here we obtain the following, a value of 0 minus 2.2 radians. So we can state sigma d equal minus the rotation at d. The minus signs means that the direction is the opposite one, so that it is anti-clockwise.